this year as last year, it's a pleasure to be here and see how things progress. As a metrology company, we're definitely looking at this progress and also tailor our instruments towards your needs. And here today I will talk about how high accuracy optical metrology can help you to make cost-efficient and very accurate devices. Okay, I will show you how this works. First, a little bit introduction about instrument systems. So we do display metrology for a long time. Today I will introduce wafer metrology also. So we're globally available with our service stations, mostly in Asia. And we do this for many years now, and probably many billions of consumer displays have been measured in mass production by our systems. So yeah, display measurement is a big thing for us. We do all kinds of display measurements, and here, of course, we want to focus on micro-LEDs. But the origin of instrument systems is an LED measurement, so we still do this, of course, and other lighting products. So the agenda here is tailored towards lowering cost by higher resolution, higher accuracy, improved takt time, and fast wafer testing. So why is higher accuracy lowering your cost? Because it reduces your error budget, and then you have less pass-fail, wrong pass-fail decisions. And higher resolution, of course, because only when you really resolve your LEDs, you can measure them correctly. Takt times, I will go into how we optimize sampling ratios to use as little size sensors as necessary, because that's cheaper. And of course, testing wafers by photoluminescence first before any kind of electroluminescence measurement, because that's much faster and cheaper. Let us look just for one slide into the first part, high resolution. So currently we have systems, camera systems and spectrometer systems. This here is an image of a MicroLED display with a 4 micrometer size LEDs, and that's the corresponding white spectrum. And here is in blue and green. And you can see that 5 micrometers is oversampled here by at least 20 camera pixels. So what I want to say here with our systems, we are sure we can provide the resolution and accuracy to look also in the state-of-the-art LEDs. And we are with our highest magnifying system, which is here, we can look at resolutions of around 300 nanometers, so 0.3 micrometers. So we think we are a little bit prepared for what's coming up next. But now I'll go a step back. We heard about the hardware. Tick, we are safe, at least from our point of view. So what's missing still, where we should have a look at metrology? Let us go back in old times where there were LCD displays. So this is of course not a real LCD spectrum, but in principle, you had 3 stimuli, red, green, and blue, and they didn't differ in spectrum very much, but only in amplitude. So that for a metrology device, like a colorimeter, is a very simple problem. When you go to OLED and nowadays to micro-LED, you have a strong spectral variation in between the different emitters. You have millions of emitters, and they are all individual emitters that might differ quite substantially. We've seen really substantial shifts here on the order of 10 nanometers, something like this. And also, bandwidth becomes very small. This is also not very good for dry-stimulus filter colorimeters. So we see this especially in all kinds of LEDs, white, phosphoric LEDs, colored LEDs, in AR, VR application with micro-LEDs and micro-OLED also, and also on micro-LED wafer testing. That's because a standard calibration is not well fitted to micro-LEDs, at least from our experience, what we look at, and that's due to the principle of similarity. because the colorimeters are calibrated